Okay, and so welcome to the 114th talk in the HoTT series. And that's not counting the summer school. Including the summer school, we have 162 videos on YouTube. This week's speaker is David Wärn from the University of Gothenburg, and his title is Path Spaces of Pushouts via a Zigzag Construction. Please go ahead, David.
Okay, thank you, Dan, and thanks to the organizers for this opportunity to talk. As I'm going to be presenting a construction that was announced already a year ago, but what's new here is the name, the Zigzag construction, which I'm trying to launch. And I haven't presented it like this before, I guess. So just to give a brief overview of what I'm going to cover in this talk. So I'm first going to give some kind of background to the problem of understanding pushouts and their path spaces. And then I will present the zigzag construction, which solves this problem. I'll present it in two different styles. And then I will discuss some applications of this construction by analyzing what I call the convergence behavior of the construction. So we will see some results about when pushouts are truncated, about the Massey theorem, and about combinatorial group theory. Okay, so I will start by just saying what is the setting I'm working in. So I will be working informally in HoTT in this talk. There's no associated formalization yet. And it's kind of a minimal HoTT setting. So we just assume pi is sigma, univalent universe, naturals, and pushouts. So just to fix some notation, when I talk about pushouts, I'm going to talk about a type family A, a type family B, and a relation R indexed by A and B. And then the pushout is the type freely generated by a map from A, which I call the left inclusion, a map from B, which I call the right inclusion, and this path constructor glue, which is that any two elements of A and B that are related by this relation are equal in the pushout. Okay, so we'd like to understand these pushout types. We know that their elements are merely either of the form in left of A for some A or in right of B for some B. And then the next question one can ask is kind of how are these canonical points identified in the pushout? So what are the identity types or path spaces between them? And there's kind of three kinds of identity types you can look at. There's the ones that are kind of mixed, in left equals in right. The one that stays in left, so in left A0 equals in left A, and the one that stays in right. And I'm going to be talking about the first two kinds just for the sake of notation. So the third is really a special case of the second, with the roles of A and B swapped. But for the purposes of this talk, we're going to have some fixed element A0 of A, and we compare in left of A0 with the in right of B and left of A. And just to say that this problem isn't completely trivial. So usually when you look at sort of basic type formers in HoTT, we can, in some sense, very explicitly understand their identity types. But for pushouts, the situation is a bit more complicated. So, for example, you can build spheres like Sn just as iterated pushouts from very simple types, but they become very complicated and they're not even truncated for any age level. So it's kind of a challenge to understand their identity types or higher identity types. Okay. So to give a kind of a naive explanation of what are these identity types like, so we have the generating paths coming from this glue path constructor. So whenever A and B are related by R, they in left of A equals in right of B. We have this map. But aside from these elements given just by glue, we also have things, well, the inverses, and anything kind of built up as a composition of these basic things and their inverses. So we have these general kind of zigzags between A and B. And you can show that any path is merely a composition like this, but there are also some, so we want to understand the full space, the full path space. So we have to kind of consider some kind of inverse laws that if you take a basic path glue R and composed with its inverse, you get reflexivity. So this is some kind of inverse law. You have the quotient pi, but it's a bit unclear exactly how do we go about this quotienting in a correct way. So if we simplify a bit, and for example, we look at just the set truncation of this path space, then the situation becomes a bit more simple. And this is the setting of so the Seifert-van Kampen theorem, which has been formalized also in HoTT by Favoni and Schulman. So this is yeah. And so there's also a more precise description of these spaces given by Nikolai Kaus and Jakob von Ramer. So they give a universal property, or they call it an induction principle for the path spaces. And the idea behind this is kind of simple enough that I can try to present it in one slide. So in general, if I have any type X with a point little x, we have this type family given by identity types with little x. And the universal property of this type family of the identity types says that it's freely generated as a type family by reflexivity. This is what the J rule expresses, if you like. Okay, so this is the general story. And then if we specialize to pushouts, the situation is a bit, we can say a bit more. So we know that a type family over pushout, well, it's a map from the pushout into the universe, and assuming univalence, this is the same thing as the data of a type family over A, which I call P, a type family Q over B, and this data of equivalences, E. So whenever you have two elements of A and B that are related, then the type families P and Q at those points are equivalent. So this is using the universal property of pushouts together with univalence, if you like, or it's a kind of encapsulation of descent, if you like. Okay, so if we combine these two observations, essentially what we get is that the triple PQE as above, which is freely generated by a point above A0, is, well, there's a unique such thing, and it is the identity types. So with in left of A0. And this picture, so B and Q correspond to these identity types, and E corresponds to post composition by this glue path constructor in this picture. Okay. So this is a very nice description, and it's easy to prove, and you can do a lot with it. And they have some applications in their paper, but it's kind of limited. So there are some things you would like to prove where it's not immediately useful. And you can kind of tell that something strange is going on in that it describes path spaces of non-recursive hits, so pushouts, as recursive hits. And recursive hits are much more complicated than non-recursive hits. So in particular, it's not clear that you could iterate this construction to get an understanding of the higher path spaces. And the recursiveness comes from this equivalence E going between two of the types that are being inductively generated. So if you think of E as a map, it's a recursive map from P to Q. And well, together with its inverse from Q to P, so you can go back and forth. And here there is a close analogy with the James construction, so which is expressed and formalized in HoTT by Brunerie. So I want to make this precise, so I just start by briefly kind of sketching what the James construction does. So this will not be exactly important for the construction later, just to give some kind of motivation or to set the background. So the premise of the James construction is that you have some pointed connected type X pointed by X naught, and then you take the suspension, which is some particular kind of pushout, and the James construction describes the loop space of the suspension. And there's a recursive description of this loop space, Jx, which says that it's freely generated by a term epsilon, which corresponds to reflexivity or the neutral element, a map alpha, which is some kind of action by x on Jx, so it corresponds to precomposition by some generating paths in this loop space. And then there is some kind of unit law delta, saying that the base point acts like the identity. So this is also like Carlson-Ramer's description. It's a recursive description. What's recursive here is the map alpha, which takes an argument of Jx and returns an argument of Jx. But what's nice is that this can be unrecursified, and this is something that Binary describes. So what does that mean? It means that Jx can be expressed as a sequential colimit of types J and X, where the J and X are defined using non-recursive hits, pushouts. And explicitly, this recursive point constructor alpha from Jx to Jx unrecursifies to some alpha n, which now goes from Jnx to Jn plus 1x. And there is some naturality condition which ensures that this map at the level of the terms of the sequence actually induces a map on the sequential colimits. And then there is some more stuff to the Jnx, but I don't want to talk about this now. So what we want to do is we want to follow roughly the same strategy of unrecursifying Carlson-Ramer's description of path spaces of pushouts to get something more useful. So we want to describe these types PA and QB, so the identity types with in left of A. We want to describe these as sequential colimits of PNA and QNB. We want to build some kind of approximations to them using non-recursive hits, and then the colimits should be the right thing. And the question is then, so before we could unrecursify a recursive point constructor, but in Carlson-Ramer's description, we have a kind of a constructor for an inductive type family that's given by a family of equivalences. So the question is, how do we unrecursify an equivalence? And I will mention some ideas in this direction. So you can kind of express equivalences as maps with together with some homotopies. And this basically allows you to express hits with these equivalence constructors in terms of hits with just ordinary point constructors and path constructors. And for this, you want some kind of description of what is an equivalence. So Carlson-Ramer say that equivalences are bi-invertible maps and give some explicit hit for a description of the hit in terms of just point constructors and path constructors using bi-invertible maps. In another paper by Reike, Schulman, and Spitters, they use what they call path split maps for another purpose, but to solve the same problem. And I believe one could start from these description of equivalences and somehow unrecursify them to get some kind of sequential colimit description of these types. But it seems like the sequences one gets are not the right sequences, even if their colimits are correct. So instead, we follow a different route. So we do something else. And the idea behind it is basically how do we get an equivalence between two sequential colimits? So here is one way. So suppose you have two sequences, P and Q of types. So P0 is some kind of sequence of types indexed by even naturals. I have P0 mapping to P2 and so on. Q is some sequence of types indexed by odd naturals, Q1 mapping to Q3 and so on. And suppose I have some commutative diagram where at the top row I have the sequence P, in the bottom row I have the sequence Q, and then I have some interleaving maps in between with commutative triangles. Then the lemma, which is really some kind of construction, is that induced by this diagram, there is an equivalence between the colimits, the sequential colimits. And you can kind of, I don't want to spell it out exactly, but you can kind of guess what this map does. So, I mean, this diagram, if you forget about the maps going up and right, it's a natural transformation of sequences, so it induces a map on sequential colimits, and that's basically the forward map. But I give a kind of more conceptual proof sketch of why you have this equivalence. So you can form the full sequence where you include both P and Q alternatingly. And then it's a general fact about sequential colimits that the colimit of any sequence agrees with the colimit along any subsequence. It's a fact about final functors, if you like. So if you take this sequence containing both P and Q, both the sequence P and the sequence Q occur as subsequences. So actually, all three of these sequences have equivalent colimits. In particular, P and Q have equivalent colimits. Okay. So this is going to be kind of the input to the construction. And then the idea of the construction is as follows. So this is now the zigzag construction. And the idea is so simple that it fits into one slide. So as before, we suppose we have two types A, B, and the relation R, and we have some base point A0 of A. So we will define sequences of type families P and Q over A and B freely on the following data. So we will have a map Pn to Pn plus 2, a map Qn to Qn plus 2, a term of P0, A0, and for any AB that are related, we have this kind of interleaving diagrams between the sequences at those points. So essentially what this does is, so these Pn's and Qn's will be some kind of approximations to their colimits, to the path spaces. So if the path spaces contain somehow all possible zigzags, then these Pn and Qn, intuitively speaking, contain zigzags of bounded length. So Pn will contain only those zigzags that can be expressed as a composition of at most n edges or n generating paths. And similarly for Qn. So the reason why P is indexed by even integers basically is this fact that if in a bipartite graph you want to take a path from one part to the same part, then you have to use an even number of edges. And if you want to go from one part to the other part, you have to use an odd number of edges. That's why Q is indexed by odd integers. So this diagram, the maps in the diagram are basically expressing that you can take a path of length n and then append an edge, and then you have a path of length at most n plus 1. And the horizontal maps are just expressing that any path of length at most n also has a length at most n plus 2. Right, and so just to stress that in this diagram, the top and bottom row are the maps are the ones given before that don't depend on. So the maps in the top row don't depend on B or R, but the rest of the diagram does. And so somehow commutativity of these triangles expresses that if you add an edge and then it's reversal, then you haven't done anything. Okay. Yeah, so this is basically the universal property of the construction, but more explicitly, what are the types involved? So and why is there such a freely generated thing? So I will start by describing the first two type families. So P0 intuitively should correspond to paths of length at most 0. And there's only one such thing, which is the empty path. And there's one from A0 to A, well, only if A0 equals A. So this is just identity type. A0 equals A in the type A that we started with. Similarly, Q1B is paths from A0 to B of length at most 1, and there's just one such thing for each generating path. So this is just the witnesses that A0 and B are related by our relation R. And then generally, this type PNA is defined recursively in terms of the previous two type families. So it's given by this pushout. So the bottom map here is saying that, well, we have this map PNA to Pn plus 2a, which we discussed before, and it's there by construction. the right vertical map expresses that you can append an edge to a path of length n+1 to get a path of length at most n+2, and then the path constructor in this pushout, or the commutativity of the square, is expressing that if you add append an edge and then its reversal, then you get the same path that you started with. Yeah, so Pn+2a is given precisely by this pushout square, so it has kind of exactly the properties we need and nothing more. And so the map Pna to Qn+1b here is in the context where we have an element of RAB is also the one on the previous slide in the interleaving diagram. Okay, and similarly, so
David, maybe you should also say the vertical map on the left is just the projection, right?
Yeah, thanks. Yeah. The vertical map is the projection. And recursively, there's a map. Okay. So I just want to say this construction is essentially symmetric in A and B. So Qn+2b is defined in exactly the same way, just changing the roles of A and B. So it's given by the same kind of pushout squared. Okay, and there's some duplication here. So the fourth case here really covers the second one. If you take n to be -1, you just have to understand that Q -1 of b is defined to be the empty type, basically because there is no path of length at most -1. Okay, so this is basically the construction. So implicitly here there are these maps, Qn+1b to Pn+2, or the map of Pna to Qn+1b is the one that's basically comes from this right vertical map in the previous stage. Okay. So this is how the sequences of types are defined. And then we have this theorem that, so with the same notation as before, these sequences have the correct colimits. So their colimits are at spaces in the pushout with in left of A0. So this is, I mean, the reason why it's a reasonable construction. And I just give a rough proof sketch of this. So, I mean, there are, I think, several ways you could, a couple different ways you could go about proving this exactly, but in particular, you could appeal to Kalson-Rarmer's universal properties. So, if we denote by P infinity the sequential colimit, and in the same way, Q infinity is the sequential colimit of Qn, then so we have these equivalences between the sequential colimits, this ER, whenever we have a witness that A and B are related. And this is the one, the equivalence induced by this interleaving diagram. So it's this lemma we had before, that for an interleaving diagram between sequences, you have an equivalence between their sequential colimits. So at least we have this data, P infinity, Q infinity, E, this kind of triple, as in Kalson-Rarmer's universal property. And we have a term of P infinity A0, which essentially comes from P0, the fact that, so P0 of A0 is the identity type A0 equals A0, and there we have reflexivity. So we kind of put in initially exactly enough to get this term. And I mean, essentially by construction, I don't want to go into details, but essentially by construction, this data is freely generated by this term. So yeah, I'm claiming that it has the universal property that Kalson-Rarmer described. Okay, so that finishes the proof sketch. Yeah, and I want to show an example, which is kind of the first interesting pushout you can look at. So we're looking at the loop space of the circle. which we know to be Z. And so I'm going to try to explain how this construction describes Z, the integers. So we have this push out of 1 and 1 glued along a 2-element set, which I picture as containing some blue element and a red element. And I'm kind of sloppy here, so I'm conflating type families over the unit type and the unit type. I mean, it is just a type. So, I mean, maybe I should think of two here as a relation, but I just think of it as a type. So in the circle, we have this north pole and the south pole, and then we have two kind of generating paths, a red one and a blue one. And the zigzag construction describes two types, describes the loop space n equals n, and also the path space n equals south. And each of these is defined simultaneously, or is described simultaneously by these sequential colimits of some sequence. So what are these sequences? So you can picture north equals north as the bottom row is in this diagram. I've truncated the diagram at the left and right edges. And in particular, it has this kind of distinguished base point reflexivity, which I equal 0. And then in the top row, I've pictured the north equals south, this path space, which doesn't have a distinguished base point unless you pick a favorite element of your 2-element type. And we can picture this. So if the bottom row is the integers and the top row is the gaps between integers. And there's two sets of edges in this picture. There's blue edges and red edges that each define an equivalence between the top and bottom row. There's an equivalence which goes to the right when you go from top to bottom, and there's an equivalence, the red equivalence, which goes to the left when you go from top to bottom. And these two equivalences are correspond to the equivalences between north and south, and north equals north, north equals north, south, and north equals north, which are given by basically post-composing by the generating path. So that's one. And I claim that the filtration of these two types, so the types Pn and Qn, are given by intervals centered on 0. So first we have P0 is just this singleton 0, and then Q1 contains these two anonymous points next to it. P2 contains -1, 0, 1, and so on. So this is what I claim, and this is what I claim, and exactly how does this happen? I just show a picture which describes how P4 shows up. So I claim that P4 is a 5-element set containing -2, -1, 0, 1, 2. And essentially, by definition, I've kind of simplified a bit the pushout diagram describing it. It's given by this pushout diagram, and you can picture this as you have two copies of Q3. Q3 is 4 points, so we have two copies in this picture below, and then we glue them along P2, which is 3 points, and the two maps P2 to Q3. This red map and a blue map, which kind of shift things to the left and right. So in this picture, you can kind of see that, okay, you have kind of 5 components in the picture, and the 3 middle components, when you kind of take the push out, you get something contractible in each component, because you're taking kind of 3 points and gluing them along 2 edges. Or if you're like, you're taking 2 points and gluing them along 1 edge. So yeah, this push out is a 5-element set in this one. So this push out expresses that the 5-element set is given by gluing 2 4-element sets along a 3-element set. So that's just to illustrate the construction in a concrete special case. Yeah, and then I will say something about an alternative way of understanding the construction, which is due to Christian Sattler, and it avoids some of this type theory style indexing. So in type theory, we often talk about type families, where externally or in category theory, maybe you would talk about maps between objects. So this presentation is more in the category theoretic or diagrammatic style. So So for this, instead of thinking of R as a relation between A and B, we can think of it as a type or a living or with projections onto A and B. So it's a span of spaces, or by space I mean type. And then basically what we want to do is, suppose given some type Y with a map into the pushout, we want to understand the pullback of this span along this map. So this is some kind of diagrammatic way of understanding path spaces. It's about pullbacks. And what does it mean to pull back a span along a map? So this span maps to the pushout. So each component maps to the pushout. So you can pull back each of these three types along this map, and then you get three new types. And in fact, you have a span. So the pullback of this span along this map is another span with a map back down to this one. So the construction doesn't solve this problem for general Y with maps into the pushout, but rather for any given span with T0, T0, Q0 over A or B. So by over, I mean that, for example, P0 maps to A, T0 maps to R, Q0 maps to B, and we have two commutative squares. So given such a span over A or B, we have an induced map on pushouts. And the construction describes the pullback of the span A or B along this map of pushouts. And the construction proceeds by constructing a sequence of spans over A or B, Pn, T, and Qn, and then taking the colimit of the sequence of spans. So it's a pointwise colimit, if you like. And it's still a span over A or B. So we want to do this in such a way that this colimit is the desired pullback. And to this end, in a diagrammatic presentation, we can, this universal property of Gauss von Römer, it essentially expresses descent, but we can just use descent for pushouts here directly. So what does it mean? So it says basically that given a span P infinity, T infinity, Q infinity over A or B like this, if the two squares are pullbacks, if there are Cartesian squares, then this whole span is the pullback of the bottom span along some map into the pushout. And in fact, this some map is the induced map on pushouts. Okay, so this is descent. So we want to ensure then that these squares are pullback squares. And the way to ensure this is, so this span above is defined as a sequential colimit. And we can ensure that these squares are pullbacks by ensuring that for infinitely many stages, the map Tn to Pn is a pullback of the map R to A. And for infinitely many stages, for infinite many n, the map Tn to Qn is a pullback of the map R to B. But not for the same n's. So there will in general be no n for which both of these are pullbacks at the same time. And that's why we need to take this colimit. And so I won't explain precisely why it's enough to ensure that these are Cartesian for infinitely many n, but it's somehow about the commuting pullbacks with the sequential colimits, which is also something that we know how to do in HoTT. Okay. Yeah. So explicitly, then what does the construction look like diagrammatically? So diagrammatically, suppose we have some span PTQ over A or B. I will describe a way to construct a factorization of this map of spans. So a third span P prime, T prime, Q prime in between the two with the following property. So P prime is equivalent to P. The map T prime to P prime is Cartesian. So I'm here ensuring that this desired property kind of holds in one stage. So we have this pullback square, and I will do this in such a way that P prime, T prime, Q prime have the same pushout as P, T, Q. And basically this diagram shows how to do it. So first you define P prime to be just P, and T prime you define to be the pullback here, and Q prime you define to be the pushout here. And then it's kind of an elementary calculation that top and middle row have the same pushout. But I won't explain this in detail. So this is the way to make T prime to P prime Cartesian, and then there's a symmetric analog where you make the map T prime to Q prime a pullback of RB, where you just swap the roles of AB and BQ. Okay, so the construction then proceeds by starting from some arbitrary span, T0, T0, Q0, and iterating the previous construction together with the symmetric version. So alternating between making Tn to Pn Cartesian and making Tn to Qn Cartesian. And because in each step of this construction, the pushout is unchanged, you can kind of show that also in the colimit, the pushout is the same, basically by commuting colimits and colimits, sequential colimits with pushouts. And then we get this desired result that the sequential colimit is precisely the pullback of the span along the induced map of pushouts. Where this one is the pushout which is unchanged throughout the process. So it's also the pushout of this final colimit span. And for example, then if I start from the span which is A00, then this pushout is just A. So then I get the pullbacks of A and A or A and B with the projections into the pushout. So that or maybe I can take if I have a base point of A, I can take the span. I can start from the span which is 100, and then this recovers the construction as I presented it before in this type theoretic state. Okay, so I mean it's the same construction presented in two ways. Okay. Yeah, and here's a picture just showing the first few steps of this diagrammatic perspective. So starting from the span A00, this just shows what happens when you alternate these steps. So you can see kind of the first few rows are simpler, and then it becomes more complicated to write down in this notation. And I've marked here the edges that are Cartesian over the underlying edges in the underlying maps in A or B, as well as the squares that are pushouts. Okay, that's I think what I wanted to say about the diagrammatic presentation. So now I will say I will try to describe the kind of analysis of this construction, which leads to the results, the applications of this construction. So yeah, this is what I call convergence behavior. So essentially what we're trying to understand here is, so we have some sequence of types Pn that converge to some colimit P infinity that we're interested in. And the question then is, well, how well do the terms in the sequence approximate the colimit? So another way of putting this is the kind of how close are the terms to each other? How much changes when we go from one term to the next? Or put differently, how far is the map Pn to Pn plus 2 from being an equivalence? If this were just an equivalence for all n, then it would mean that nothing happens really in the construction. It just converges or terminates directly. And of particular interest are the maps P0 to P infinity. So P0A is the identity type in our type capital A, A0 equals A. P infinity is the identity type in the pushout in left A0 equals in left A. And this map, it turns out, is the actional paths of in left. So this is some natural thing that shows up as one of these maps. And similarly, Q1 mapping to Q infinity is the glue constructor. Yeah. So these are kind of two of the maps that we want to understand in the end. So later I will have some kind of more technical lemmas in this direction, but I want to first offer a kind of attempt at explaining informally why we have some kind of results. So essentially, so we want to understand the maps Pn to Pn plus 2. And in particular, we want to kind of give some kind of descriptions of the fibers of these maps, saying that the fibers aren't too complicated or that the fibers have some kind of properties. And these fibers somehow express when a zigzag of length at most n plus 2 happens to have length at most n. So if you imagine you have some zigzag of length at most n plus 2 with some kind of composite of n plus 2 generating paths, to show that it has length at most n, what you have to do is basically have to be able to reduce some pair of adjacent edges in this list. And by reduce, I mean essentially to apply a kind of inverse law. So you can only do this when you have an edge followed by its inverse, or it's the other way around. And the ability to reduce like this is controlled by identity types in these types. So for a B and B, you can look at the type of A together with an edge, A and A together with an edge to B, or vice versa. Given an A and A, you could look at the sigma type of B and B together with an edge to A. So these identity types somehow express when two edges are equal in the appropriate sense, and so when we can reduce like this. And these two types you can think of also more diagrammatically as being basically the fibers of the diagonals of the maps of the projections R to B and R to A, if we picture R as a total type. So if we picture this relation instead as a span. So I will be kind of sloppy and switch because I don't have a good notation for associated with the relation R, the total type of all A and A, B and B with which are related. Yeah, and I want to stress this that so it's you have some list of edges, and to show that it has length at most n, it's enough that you're able to reduce one of these adjacent pairs, and there's some kind of choice roster or confidence property which should show that whichever one you choose to reduce, you end up with the same reduction in some appropriate sense. So there's some kind of disjunction going on here, and roughly speaking, I would say this is why we see joins of these identity types showing up. So joins of spaces are some kind of homotopical generalization of a disjunction of propositions, as I understand it. Okay, so this is some kind of informal explanation of what's going to happen. So now for a more precise description. So right, so we want to understand the maps P and A to Pn plus 2A. And by definition, this map is defined as a pushout of another map. It fits into this pushout square, where the top map is this more complicated thing. And this map does nothing on the first two components. So basically what's interesting is the map on the third component. So the fibers of this map are just the fibers of this map. But basically we want to understand this map, P and A to Qn plus 1B, which is appending one edge. And then there is this precise theorem, which is a bit hard to parse maybe. So it says that this map, Pn to Qn plus 1, is the pushout of another map, F, where the fibers of F are joins. Each fiber of F is the join of a type X and a type Y, where X is the fiber of this map Qn minus 1 to Pn. So that's the same kind of map, but swapping the roles of A and B and going to the previous stage. So that's X, and then Y is some identity type. And I write it very explicitly here, but this is an identity type of the form mentioned on the previous slide. So it's in this sigma type of, I mean, we have some A, and then these are two terms in the sigma type of a B and B with an edge to A. Okay. And so because everything kind of treats A and B the same way in the construction after the first step, we have the same theorem also for the maps Q and B to Pn plus 1a, just swapping the roles of A and B. So this means that we can kind of recursively apply the theorem. So this part describes this map in terms of this map, and then if we change n, we can go back and forth between these two maps. Okay, so that's that was a more precise theorem, and then here's a kind of coarser but more easily usable theorem. So if we want to show that these maps have some property, Pn to Qn plus 1, or Pn to Pn plus 2, or Pn to P infinity. So we want to show something about these maps. Let's suppose, yeah, we have this general theorem in terms of arbitrary classes of maps. So if for each n we have some class of maps Cn with some constraints. So I ask that each of these classes is determined fiber-wise. So Cn consists of those maps, all of whose fibers have some property Tn, or Tn is some property of types. So this is the case, for example, for maps that are truncated or maps that are connected. I ask also that each class of maps is closed under pushouts. So remember before on the previous slide, we have that the map we were interested in was actually the pushout of another map. Or this happens twice actually, but we have to kind of pass to pushouts. And so many important classes of maps are closed under pushouts, like connected maps or embeddings or equivalences. I ask also that T-1 contains empty type, and that Tn has this closure under join. So if you join some type in Tn-1 with an identity type of one of these two forms, depending on if n is even or odd, if any such join should lie in Tn. Okay, and then the conclusion is that all these maps from Pn into Qn plus 1 or Pn plus 2 or P infinity lie in Cn. Well, okay, for the last part, for the maps into P infinity, we need some extra condition about these classes being nested and closed under transfinite composition. Okay, so that's the very general theorem obtained from this construction, which we then can instantiate with lots of different classes of maps to get interesting results. So now we're reaping the rewards. So for the first application is rather more simple than the next one. So this is a result which has been proved in HoTT, first by Eric Finster, I think, and then also by Klaus von Römer. So for this, we suppose the projection R to B is an embedding. So essentially, we're assuming that every element of B is related to at most one element of A. Then it means that the diagonal of this is an equivalence. So its fibers are contractible, and whenever you join a type with something contractible, you get something contractible. So in this case, we can take Cn to be a very small class of maps containing only equivalences for n at t0. And the theorem on the previous slide applies. So because equivalences are closed under pushouts, and because of this condition about the joins with contractible types. And then we see that app inlel, which is this map P0 to P infinity, is an equivalence already. So this means that inleft is an embedding. So this is the statement that embeddings are closed under pushouts. And there are also some more consequences. So we can see that the pushout square is a pullback square because glue is an equivalence also by the same reasoning. And we can also get this result describing so the map. If instead we assume that R to A is an embedding, it won't be true that in left is an embedding in this case, or in left won't be an. It won't be an embedding in general, but we can still describe this type in left A0 equals in left A. It has some very explicit description, which basically expresses that in this case, it is just P2A kind of expressing that you only need paths of length 2 to describe general zigzags in this case. Okay, but I don't want to say any more about this. And as a corollary of the previous, using this, we have the following more interesting result, which was not previously known in HoTT, which says that if both projections R to A and R to B are zero truncated, meaning that their fibers are sets, or their diagonals are embeddings, then the same holds for in left and in right. So they are also zero truncated. And moreover, glue is an embedding. And the proof of this, it's also an instance of the very general theorem about classes of maps, where we take each Cn to be the same class consisting just of embeddings. So there we use this fact that embeddings are closed under pushouts. We use also that so embeddings are those maps whose fibers are propositions, and propositions are closed under joins, contain the empty type. So there's something funny here because well, you can think of embeddings as n-truncated maps, or n is -1, but in general, there's no reason to expect that n-truncated maps would be closed under pushouts. For example, you can build S2 as the pushout, or the suspension of S1. But for embeddings are closed under pushouts, and so we have this result, but it's kind of, there's something special about it. It doesn't generalize to higher truncation levels. And I just want to remark that the same result holds also if we replace embedding by complemented embedding, by which I mean a map whose fibers are decidable. And so true or false. And basically because decidable propositions are also closed under joins, and complemented embeddings are closed under pushouts. That's kind of direct. And we also have this transfinite composition condition. And so this the version of the theorem with the decidable embeddings expresses some kind of, it has some computational constructive content. It's a kind of a decision algorithm on testing equality of words, is one way to understand it in some kind of. Well, I will give an example later what all this has to do with group theory. And just to remark, well, a corollary of this is of the previous theorem is that if so if again we assume that both projections R to A and R to B are zero truncated, and we suppose also that A and B are n truncated for some n at least one, then the pushout is also n truncated. And the proof is very direct from the previous results. So we just observe that to be n truncated means that the n+1 loop space at any point is contractible. So we have to understand the higher loop spaces of this pushout, but by the previous result, in left and in right induce equivalences already on the second loop space, so also on higher loop spaces. So whenever we have some understanding of the higher loop spaces of A and B, we get one also of the pushout. So in particular, you can take n here to be 1, and then you can take A or B to be any sets. A map sets is zero truncated. And then you see that, for example, the suspension of a set is one truncated. So this special case resolves an open question in HoTT that was mentioned already in the HoTT book. And it's a result that was for a long time expected to be not provable in HoTT, even though it was known in some external sense for spaces and for higher topologists. Okay, and yeah, okay. So I just want to give a sketch of what this has to do with group theory. So this is an observation due to Buchholz, de Jong, and Rijke. So there's this result in combinatorial group theory about what's called H and N extensions, where you have a parallel pair of group embeddings. So you have two groups H and G, and you map H to G as a subgroup in two different ways. And then there's this group you can construct, which is called the H and N extension, which has some universal property, and there's an important result that a particular map from G into this HNN extension is an embedding. So normally this is something you prove in kind of a combinatorial way and often in a non-constructive way. And so it turns out that it just follows from directly from these results. Basically because at the level of the loopings, this HNN extension is a co-equalizer. It's the colimit of this diagram of the loopings. And so I haven't talked about co-equalizers before, but they are a kind of non-recursive hit, and they can be expressed as pushouts in this way. And in this way, you can see that. So the assumption that HG is an embedding means that the map BG is zero truncated. So in this diagram, both the legs of the span are zero truncated maps. So by the previous theorem, all the maps in this square are zero truncated. So in particular, the bottom map is zero truncated, meaning that the map of loop spaces G to the HNN extension is an embedding. So yeah, what's nice about this proof is that it's directly constructive and avoids any kind of tedious combinatorial reasoning. Okay, and then to give a final application of kind of a different sort, we can also prove that the Blaker's Massey theorem, which of course has already also been proven in HoTT by a nice argument by induction, which kind of also shows something a bit stronger than the classical statement. And yeah, in this way we can prove the same thing, but with less work, because it kind of directly follows from this general result. So the theorem says something about if you assume that you have a span ARB where the both predictions R to A and R to B have some known connectivity levels. So R to A we assume is K connected, and R to B we assume is L connected. Then the conclusion is that glue has also some kind of connectivity level. And this is basically what we get by taking Cn to be success of connected maps for some H level, for some appropriate H level, using the fact that connected maps are closed under pushouts and this join connectivity result, which says that the connectivity of a join increases with the connectivity of each factor. Yeah, and I should say that this result in this argument directly generalizes a corresponding argument with the James construction, which is in Pinner's paper, where he also proves that the maps in his sequence, which approximates the loop space of a suspension, those maps also have some kind of increasing connectivity levels. So that was yeah, I mean an inspiration in finding this generalization to the case of pushouts. So I mean all of this generalizes really the James construction in the sense that the James construction is about a very particular kind of pushout, namely the suspension of a pointed connected type, and everything here applies more generally to arbitrary pushouts. But we still have the same kind of nice results like this analysis of convergence behavior, which in the James construction leads to the Freudenthal suspension theorem, and in this case leads to the Lakers Massey theorem, among other things. Yeah, and that's the end of my slide. So there's a rough preprint available on my website for some time with perhaps some more details of these arguments, and there should appear a better preprint soon. So yeah, thanks for listening.
Great, thank you very much, David. So we'll do our usual silent applause or using the reactions button in Zoom. And we're right on time, so we have plenty of time for questions. I'll open the floor. Okay, I'll get the ball rolling then. So you mentioned that it hasn't been formalized. Is there any parts that have been formalized, or is there plans to do that?
Yeah, I mean, not really. So I mean, there's a lot of inputs to the, I'd say, yeah, I did start trying to formalize it, but I ran out of steam quite quickly. So there's a lot of, I mean, for the analysis, there's a lot of things like we want to know things about this commutation of pullbacks and sequential colimits, and yeah, so there's a lot of even before formalizing any kind of new part of the construction, there's a lot of prerequisite results that should be formalized in one place. So a lot of things have been formalized in different places before.
Yeah, that's exactly what I was thinking. Like, oh, this part I know where it's done, and this part I know where it's done, but we have a bit of fragmentation, and yeah. So anyway, well, maybe some people will be willing to help do some of the background work. That would be great.
Yep.
Other questions? Was everything just so super clear and elegant that it leaves no doubt about anything? Can you say, oh, okay, please go ahead, whoever just unmuted.
Okay, yeah, so I have a silly question. So when you call the zigzag construction, what exactly does zigzag refer to? Because on the one hand, you have like zigzag of edges that build up a path, and on the other hand, you have this nice diagram with a zigzag in it, right?
Yeah, this is a tough question. So I mean, I think it can refer to either one. So, and there's some relation between the two, I guess. But I'm a bit ashamed to call this a zigzag because I guess in category theoretic terminology, it's not in the sense that the arrows are all pointing the same way. I mean, yeah, I would like to call this a zigzag. Yeah.
Mm-hmm. So it's the zigzag construction because it describes types that can be thought of as being inhabited by zigzags.
Yeah, I would say this.
Okay, great.
But also there's a zigzag in this diagram, I would say.
So while you've got that diagram there, it's sort of remarkable that it automatically encodes the inversion relation that you mentioned that you're going to need. But I guess, I mean, there's more than just that. Like the full infinity groupoid structure somehow gets all handled without any need to put it in by hand. So it's not really a question, just a comment, or maybe you have some thoughts about why it manages to do exactly the right thing.
Yeah, I know it's hard to say, but yeah, there is something remarkable about the diagram. That, I mean, you could also say that so each of these triangles encodes some kind of inverse law, and naively you would expect that you have to also put in some naturality condition, which is captured by the commutativity of these composite squares. But in fact, naturality is just the composite of two triangles, composite of two inverse laws.
Yeah, there's no higher coherence. That
Yeah.
You only need one cells in that diagram.
Yeah. Yeah.
Or all right, two cells, I should say. Yeah. Depending how you.
But it's somehow like similar with the James construction that actually it never mentions associativity or a pentagon axiom because it just that starts from not composition but kind of this prepending basic generators. There's something similar here that we don't have a general composition operation, just post-composing by basic edges, and we don't need so much coherence. Yeah. But definitely it does somehow say something about infinity groupoid structures.
Okay, more questions? Plenty of time. Do you have other applications in mind?
Yeah, I mean, yeah, one application which I haven't thought out in detail, but which should work is that if you're trying to describe pushouts in terms of the simpler things, then this construction kind of takes you a part of the way there, because you can describe at least the path spaces of pushouts in terms of simpler things. And yeah, so this is if you want to describe n truncations of pushouts in terms of univalent universes, kind of sequential colimits. I see a question in the chat from Ingo. How did I arrive at this construction? And yeah, I mean, so I arrived at it in roughly the way that I outlined here, that I was trying to unrecursify Chaos von Römer's description of path spaces, and I actually initially tried to use something like these two ways, and I noticed it didn't work, and then eventually I found this simpler way.
Oh yeah, that reminds me. Go back to that slide. I was. You say that you could unrecursify these, but they seem to give the wrong sequence. What do you?
Yeah.
Can you say more about that?
Yeah. So by wrong sequence, I mean that, for example, if you start with a span of sets and you want to understand the pushout, then by these results, PA and QB in them should be sets. So you would expect that you describe some sets as colimits, so you would expect that the terms of the sequence are also sets. But this doesn't seem to be the case if you use these descriptions.
So
and this is what I mean.
Right. So maybe one way to say it is that you would get some PNAs and some QNBs whose colimit is the right thing, but they're not as useful. They don't, they don't have good properties that let you prove things about their colimits.
Yeah, so wrong is kind of a provocative, or I'd say.
Yeah.
Very
Okay.
technical, but
well, that's very interesting.
And you can kind of understand it as, so I mean, one way to see it is that if you look at bi-invertible maps, you have some map with two inverses. And these two inverses happen to be the same. But in order to show that they are the same, you have to reason about longer strings of applications of these functions. So you want to prove something about just these two maps, but you have to go to these applications of three functions to prove it. And somehow what's going on in this construction is that everything happens at exactly the time it needs to happen, as I understand it.
Okay, any final questions? Okay, well, let's thank David again. And our next talk is in 2 weeks, and it's Ingo Blechschmidt. So I'm looking forward to that. See you then.